beautiful, I have slides. I'm so excited by that. I was petrified that I would not have slides and I'd be doing exactly what you were doing. So this is a great moment to start off with. So I'm Suzanne, I'm a customer success architect at Neo4j. And essentially that means that I'm there to make sure that Neo4j delivers on the promise for which it was bought, which sometimes, and particularly for data engineers, you wonder whether products actually do that when someone hits the button and says buy. We're actually there, and my team is there to make sure it happens. So to start off a little different, time for an experiment. I have some questions for you. So how many of us write data to a database? Hands up. Oh, good. This should be everyone. But, I was expecting a couple more, but there were some no's. All right. And how many of you use an ETL tool to write data at velocity to your database? Awesome. How many of you have experienced locking of a row of data when you're writing velocity? Yeah, it's annoying, right? And then how many of you who have experienced node locking actually believe that the way you store your data can fundamentally affect the speed at which you can write new data to your database while continuously serving your customers? Oh, good, no one. And that's because this is a fundamental problem that we've all had in our lives. And database storage techniques are not usually something that you think of when you're looking at preventing node locking. That's what we're going to try and get to today. But first up, Neo4j is a graph database. Essentially, what we do is we store data as a knowledge graph. This is a system where there are entities and relationships between those entities. So we're actually storing the relationship natively against the data to give you deeper context, richer information, and essentially more descriptive power to explain what your data means and what your data means to each other. And you can use this for many, many different types of applications, quite flexible here. So semantic conventions, entity resolution, when you've got those de-identified data sets and you have to join it back together to go, this is really one person, but it might be 5 IDs. Right through to operational transactions, high velocity processing of sales as they come through the door at betting agencies, at share institutions. Singular events that need to be processed in great detail and then sometimes stopped or changed as they pass through your doors for compliance purposes. And then we're getting into the bright new age of ML predictions and AI. And of course, you can use a graph database and the enriched context you have to also produce better and brighter calculations and predictions with your AI and ML. At the core, we're looking at these round circles which we classify as entities, and then the relationships, the lines that join these two things together. So this is pretty intuitive, right? You've got an employee, you can describe them as an employee or an analyst. There's descriptors that sit underneath that entity. And that entity has a relationship with another entity, in this case, a company. And you can put descriptors on those relationships too. Key thing about relationships, they must have a direction. They must have a direction because everything has a flow. When you think of path walking through a model, we have to know which way we're going here. Otherwise, you can walk around in a circle for a really long time. That isn't to say that you can't have relationships that run in both directions between entities, but then we want a different descriptor to support that activity. So this looks pretty simple and also quite intuitive when you think about what you're doing with storing data and the data that you're keeping. Normally you'd see this as an employee table with lots of information about your employee that you then have to link to a company table and then maybe a location table as well. Here we're saying if you're going to run queries often on any form of data that says, I want to know where all of these employees work, I want to know how many employees they are and which cities they live in, and you're going to repeatedly run this analysis, instead of using your compute power to join tables together, let's actually store the joins with the data. And that way, when you run any query to run those simple sorts of analytical workloads, you're using less compute and deriving the answer far more quickly than you might imagine. So when we look at the standard types of databases that we have, we just talked about the fundamentals of what a graph database is. Relationships aren't handled well in relational databases, those tabular structures. You have to join things together, usually with an ID. And then we've also seen the rise of things like data document databases, where they don't really handle relationships at all. They're stores of information. You can mash them together, but you're also not really preserving that enrichment that comes with a native storage of information and relationships together as one. So as you can see here from the slide, queries can run up to 1,000 times faster and also scale up. The more hops you do, often the faster we get, which is the antithesis of what you might be used to seeing in a relational database. This is not a new thing, and if we're looking at where GraphDBMS sits against other types of databases, it is the fastest growing database category we've seen for over 10 years running now. So this is a real thing, and it does scale. Quote from Gartner, Graph enables people and organizations to quickly and easily uncover hidden relationships and patterns across billions of nodes of connected data. And we do see this, that it's quite easy and quick to get started with Graph. It's quite intuitive. You could see from that example that we looked at earlier, everyone knows intuitively that employees are linked to companies, and vice versa. This isn't a new concept. We're just actually enshrining that in the way that we store the data so that we can proactively use it to get deeper insights. So how do we start with a Neo4j stack? You start with a database instance, and that, of course, contains your mesh ball of nodes and relationships. And this is, of course, an ACID-compliant database, which brings me back to my wonderful point about locking earlier. If you're making a change to any node or relationship, you have to do that in an ACID-compliant way. We don't allow you to have any complications with the way you're loading your data, but we'll come back to that. Then you also have native graph technology, apps and analytics that surrounds this concept of a database. We give you drivers and tools to connect to any other sort of system that you have in the way that you'd like to do it. So we do support 10 different languages, including Go, Python, all those fun languages, C, Java, wonderful things like that. And you can use them as a developer from the outside in or as an admin. Coming up and building up the stack into the business users side, we also want to give our business users the ability to discover from a single anchor point in the graph. So you might know where you want to start, but not necessarily where you want to end up. So we do offer you visualization tools in Neo4j Bloom so that you can click by click go through your graph pathways out and see not only where you started, but where you might end up. And that's quite useful for both data analysts and data scientists, particularly as you're experimenting with this idea of connected data. You really need the opportunity to be able to see it and interact with it step by step. And then lastly, our data integration pieces. Once you get really confident with your graph model, you do want to be able to exchange data and update data at velocity. So we have connectors for Kafka, Spark, and then also database connectors for Snowflake and BI tools such as Power BI and Tableau. Great stack, looking really good, right? Everyone's confident on their graph. So when we scale with graphs, a knowledge graph codifies information, essentially, the same way as any database does. But as our data grows and as we start using our graph more, we'll naturally grow into massive graphs. Graphs do scale quite quickly. We see people with terabytes of data sitting in a single Neo4j graph. And we can support that at scale. It looks fabulous, by the way, at a distance. So something like this, really cool to look at. It makes the great cover for a magazine. It doesn't really tell you that much when you get under the hood, so we do kind of have to get away from the beauty of this. But when we come back to node locking, we're essentially saying that our entities are joined. Is this a good thing or a bad thing for node locking? Hands up if you think it's a good thing. Okay, great. That's good. And a bad thing? Not really sure. It's a bad thing because you're not only locking one thing at a time. If you've got a relationship between two objects, you're actually locking both of those things. And when you have a massive graph with fast-moving data, you can actually have a lot of retries going on if you're not careful with your modelling. So we suddenly got this tool that we love, this enriched context that we really need, and now our data analysts need it too. So what do we do about node blocking? How do we get fast data into a graph, especially when at scale? All right, so we do have some options for scalability with Neo4j, and we're always thinking about this. Our latest release, Neo4j 5, has introduced this concept of autonomous clustering, so you can scale out horizontally as well as vertically. Within that landscape, we've also introduced the notion of Neo4j Fabric, which is essentially a sharded database where you're breaking your graph model into discrete components and then joining them together with a federated layer. This may look like it's complicated, but there are actually very good reasons to do this, and it can be highly performant. So an example of using Fabric is our trillion node or entity graph that we have. So this is 3 billion users and over trillions and trillions of relationships. And what we see with this graph model is there are some entities in the graph, people in this case, they're pretty static. They don't update themselves a lot and they're not fast moving. You generally know who your users are. While you have new users coming in and out of your system, their attributes are pretty stable. You're not really updating them often. But you also have some really high velocity data running alongside those entities. You have forum posts, for example, clicks and activity. If you're there on a website, you might have interactions with other people and they might come in and out. So you've got this incredible amount of metadata that is going to scale super fast. Most of your queries are going to want to be run off your person node, but you are always going to be locking that thing if it's linked to the user's activity. So what do? By using sharding, we can actually separate these two concepts from one another. We can still link them and knit them back together, but essentially we're saying, okay, fast-moving data, you go sit in a shard. We'll load you in as fast as possible, as fast as you want, but we'll also make sure that the integrity of the person node is not continuously affected by the next thing you choose to do. And this has proven to be highly effective. So if we look at it, you can scale this out as well. So you can maintain a single person shard and many forum shards, as many as you need, and for as long as you want. So for anyone who works with sensitive data, who needs to keep their data for 5, 7, 9, or has a data retention policy of forever, and some of our clients do, you can actually do that without affecting the integrity of your new queries under this method. We even have some clients who are using sharding and saying, okay, for my older data, I'm going to use a data storage optimized instance and then a data and analytics optimized instance for my recent data, because that's where I want to do my fast queries. But I still need to keep this stuff, and I need to keep it in a way that is both inexpensive, but also to some degree accessible. So what we have here is this concept of unbounded scale, where you can still write data to your database really quickly, whether that be a person type of entity or a forum type of entity. And then also constant read performance. Whatever queries you want to run on that data, we still need to be servicing that and servicing it quickly. The one thing I will say, and for this particular example, we ended up with 19 billion nodes and relationships in the person shard and 1.2 trillion nodes and relationships in the forum shard. As you can imagine, there's a distinct difference. Even though these two things are joined together, we're actually recognizing that these two types of data have very different velocities. And any query that is run on this database at the moment, whether it's a read or write, has a latency of under 20 milliseconds, which is pretty good for the scale that we're achieving there. The one thing I will say about this approach is that you really do need to think about what you want to get in and out of your database in order for this to be optimized for you. A lot of people have come to us and said, let's go with Fabric now, because it's great and we want a graph, we've got big scale, we need to get it done right. And that is essentially true. But we do need to think about what's the type of data you're putting in and what's the speed of that. And then how are you going to want to query that at the other end of the day? So this is an example we have applied for a client in APAC, one who was very interested in this concept of fabric and sharding. They operate a route network. So this is essentially a very large shipping system, and it consists of a couple of different elements. So at the really top level, you have the route map, ports, destinations. These things are really stable. I can't really remember the last time in the global shipping network that there was a new port built. This is not something that happens every day. There's also waypoints between ports. So if you're traveling across the Atlantic, there might be 3 waypoints in between your ports. So we can section out certain different types of routes. And then you've got your assets that travel between different waypoints and different ports on the way to a destination. This can also be a holding area because there are stopping points, so you can have things stopping. And then we have the actual containers, shipping containers, boxes inside containers, those types of things. And we see that we have this same concept of different types of velocity across our data set. Containers, speeds like this. We can update anything all of the time. Whereas with our assets, updates happen maybe every couple of hours, maybe every half day, possibly every day. Waypoints, well, it's probably good enough if you're updating that every 24 hours. And the route map, also 24 hours to update. So essentially very different types of data. But if you tried putting this all in the one Neo4j graph, the amount of interconnectedness would be so high that every time you updated where a single container was, you could be locking quite a lot of things that you need to regularly draw off of. So the federated design for core routing allows for aggregation across these layers. They can talk to one another essentially through the federated layer. And we use a direct relationship between each layer to aggregate up. So it's highly unlikely that if you're asking a question of the route map, you actually need to go back to the container shard. That doesn't really happen. But because we're aggregating up container to asset to waypoint to route map, you're only ever really needing to look at anything in one place. And no update is costly. Everything's kind of sitting really nicely there. Because Neo4j, like most databases, loves small pieces of work that it knows how to do. I often say it's a bit like a runner. When you're running a marathon, if you just think about putting one step in front of the other, you're likely to get to the other end. Whereas if you're running and you're going, oh my God, I've still got 20 kilometers to go, likelihood is that you're going to start flagging and going slower. It's the same with database operations. If you keep everything small, everything's nice and fast. If you start to get too complicated in the way your database thinks about things, you will slow down. So updates in this system happen very quickly, which gives you the best proxy for real-time information. We know this concept of real-time has a lot of caveats around it, but essentially you're getting reads and writes in really, really quickly to have a pretty much up-to-date idea of where things are in the route map, which can be really useful when you're thinking about what they're going to use this system for at the other end. And it also limits how many of each type of object we have and how we control them. One of the asks for this system is we actually create a new start point every time a package enters the route map. So if we're picking the container up from your home, that becomes a new point in our route map. And it only exists for the life of the package. So we needed a way to persist that information while the container was in play, but not necessarily add it to the route map as we knew it in the top layer. So, advantages. We've talked about some of them. The foremost one is the ability to prevent locking. Because as we're updating our containers as they buzz around the world, using GPS signals, using which ship they're on, using which asset they're on, we need to be able to make sure that that doesn't fundamentally influence any other question we're asking of the graph. So we can update that container information constantly without impacting. If someone asks the graph a question like, how full am I at this port today? Or can I fit another package onto this asset? You can't be locking that asset because you're updating the GPS coordinates of a container that is on that asset. And then the information can be aggregated. So I have 10 containers on asset A. Asset A is on transit between waypoint 1 and 9. So its destination is this, and knowing where it is in the route map, you can then say where it is, when it's going to get to that place, and also how full it is. And the other thing that we wanted to be able to do is say, for a new container, these are my top routes that it can travel on to get from A to B within the route map. But I want to be able to know which one will give me the fastest result. Or if I switch midway through because something went wrong, let's say the Great Suez Canal incident of a couple of years ago where everything was stopped around the world for ages. So let's say I've got a port down and I just simply can't go there. How do I reroute everything that I've got under a what-if scenario to say, okay, let's find a different way? And if we do find different ways, how do I pick that new optimal way? How can I estimate the amount of time it's going to take? And what guarantee can I give to my customers? So the types of questions we ask, the graph at the other end, the read questions that we're asking of the graph fundamentally have to affect the way you decide to shard a graph. So I would never shard a graph based on ingestion alone. You might have data from different sources. Don't create shards just on the back of that. Because if you do, likelihood is that you're going to be bouncing around them all the time to answer any given question. That's not optimal. It'll ultimately take you longer than what it saves you. But when you have a system like this, we're asking clear questions of each shard in the data. So route map shard, which routes can I flexibly take to go from A to B within my existing network? What if? Or how much will it cost me to get from this point to this point if I take a said route? I can answer that type of question really easily, which means the business can do its job. And then what waypoints connect different ports? If there's a problem at a waypoint, if there's something that's broken down, how do we fix that? If an asset is no longer on a section of the route map, which waypoint would I expect it to cross next? So for those long crossings, if you've lost communication with something, where can you expect it to see, where can you expect to see it again? And how would that look? When would you expect to see it there? And you can answer that in the waypoint shot. Assets. Can an asset accommodate another container? So you might have already set this asset off. It might be halfway through its route map. Can it actually take another package on some or all of its waypoints? And that might affect fundamentally the pricing that you give to that person who's asking you to take a package from Sydney to Melbourne or Sydney to Japan. If you can fit it into something you've already got going and get it there super fast. And then also you can say, how many assets are in flight or benched? How much of my total fleet am I using right now? And does it mean that my total fleet needs to be smaller or larger in certain places? And then in our highest velocity shard, where is my container right now? Which route was proposed, and is that the right route for right now based on my circumstances? So lots of different layers of questions. But if you have someone who has a package in flight, thank you. So if you have someone who has a package in flight, the number one question that they're going to call and ask you is, where is it right now? And you can answer that in the container shard. Whereas if you've got someone who's calling you up and saying, I need a new package and a price for a new package, you can also do that in the waypoints and route map. So we're looking at answering different sorts of business questions in different shards in what is a highly connected and complicated data system. So it has worked out as a really good use of sharding. They do achieve very, very high velocities. over this system, and also have the ability to connect things together only where it makes sense to do so. So we are still delivering on that promise of graph where the interconnectedness of the data is still really there, but also the integrity of the data and the enrichment of it is also there. And this is a really flexible concept. As I said, data modeling and what you're actually trying to get into and out of really makes a difference in how you shard. I can't emphasize that enough. We have a client who just rolls off data between 7 shards because they need to maintain that amount of data. But they also know that the most comprehensive data that they're going to be using is the most recent. They need to keep the rest, but it shouldn't be in a graph with everything else for many reasons. It makes their reads slower, it makes their interconnectedness higher, it locks things out when you're looking at master nodes. So there are lots of different applications, and then you can also get into the cost side where you can be running different sorts of instances for different sorts of workloads. So it's very powerful, it's a really exciting space to be in. And hopefully at some point you try Neo4j and try sharding something with it.
I think we're out of time, but please, can we show our appreciation? Big round of applause.